Nice to meet you all. Good afternoon, Matthew, founder of Matrexia, where we're building what we call the memory layer for finance. Prior to Matrexia, I was co-founder and CTO of Lendflow, working with more than 75 lenders to modernize embedded finance in the SMB space. My background is in applied mathematics and data science, but my real education came from your world as a financial organization with governance, risk, and the responsibility of lending. And over the years, I've learned that prediction has never been the problem, context has. There we go. Okay. Each time we build a new model, we begin again, forgetting the financial institutions context that we already understand. In mathematics, there's a field called topology, the study of connection, that teaches that meaning doesn't live in the very points themselves, but in the relationships between them. Drawing from topological data analysis, we capture persistent shapes in data, like clusters and cycles, that endure through noise and change. When a system can make those relationships, when it can learn continuously instead of starting over, it moves from beyond prediction and it begins to understand. And that's what we want to share today, why the future of decision intelligence isn't about better prediction, but about continuity, about topology over prediction. And as you can see on this slide, machine learning predicts, but topology understands. Static models learn patterns, but they lose the continuity. Credit systems are networks that are alive, not spreadsheets. Retraining amputates structural memory. Topology evolves continuously. It never forgets. Every financial institution knows the rhythm, especially across data science. We train, we predict, we drift, we retrain, we repeat. Each model is born in the past, tuned to patterns that once held true. Then our world shifts. We retrain, we reset weights, and we erase that structure that came before. Every few months, the model wakes to a world it no longer recognizes, and we call it optimization, but really it's institutionalized amnesia. The institution remembers, but the system, the model does not. Governance, policy, market intuition, the memory we've built as financial institutions over the years is stripped away in pursuit of cleaner data. So the question we have to ask is, what if our systems could inherit that continuity? What if they could embed that institutional memory directly in their structure, retaining not just the numbers, but the relationships that give them meaning? And looking at the diagram here, this cycle of retraining restores precision, but it erases the understanding. And each loop starting outdated with accuracy resetting and that memory lost. When we flatten a graph into a table, we completely amputate the meaning behind it. Merchants, suppliers, guarantors, once connected, become isolated rows. Resilience disappears, contagion disappears, and correlation replaces causality. The model still measures risk, but it no longer understands where that risk flows from. As contexts fade, even our most trusted metrics, probability of default and expected loss, also begin to drift, not because behaviors changed, but because relationships have vanished. Topology via tools like persistent homology preserve those invariants, keeping that PD and EL really anchored to the real structure of exposure. On this slide, we can see how that flattening collapses the behavioral topology, turning those independent entities into independent rows, distorting that PD calibration and the EL consistency, which drift ultimately as structural decay, not just as noise. So rather than rebuilding models, we preserve structure. Every entity lives inside of a graph that's alive, evolving with transaction. Vector embeddings informed by topological invariance reveal that hidden similarity. A policy layer interprets those topological shifts as decision signals. Beneath it, local continuity ensures the geometry never resets. Relationships persist even as that data changes. It's not a new model, it's a new kind of memory, one that learns continuously without having to start over every 6 months. And as illustrated in the diagram, continuity is preserved through local Laplacian updates in a live Neo4j graph, with PD and EL recalibrating as topology evolves. Graphs preserve their structure, and structure preserves that intelligence. So this is what it looks like. As you can see on the slide, each orange node here is a merchant. Each pink node is a supplier. The thin gray lines are those transactions, the flat world that our model already knows. But when we see how continuity emerges, look what happens. In the center, we have Alpha Coffee connecting to Theta suppliers and Echo Fitness, which appears with shared exposure and repayment strength. On the left, we have Delta Auto and Indigo Salon from another cluster. Different industries, same structural resilience. These connections are the mathematics of memory. As patterns strengthen, PD and expected loss recalibrate automatically, not because the model retrains, but because structure reveals resilience. This is the graph that never forgets. Take a single merchant. Originally, the model scored 0.58 and declined. Over time, that network would grow. New suppliers would connect. Repayments would stabilize. Peers begin to emerge naturally. The graph rebalances and that context shifts. Maybe we assign 12 more points to it. That decision then moves from a decline to an approve. And it all happens before any default signal appears. Expected loss falls, not because the model's changed, but because the structure showed stability a lot sooner. In our pilots, this has reduced false negatives by 15%, preserving a lot of yields without adding any risk. It's all in our data. When relationships stay intact, those systems recognize resilience early, turning context drift into preserved yield. Here on the slide, this live system adapts faster than any model, with the graph expanding to reveal these stable peers and instant reclassification. No retrainings needed. Side by side, the difference is clear. Machine learning is episodic. It learns in bursts from snapshots of the past. Graph reasoning is continuous. It learns through connection, carrying knowledge forward. One reacts to drift, the other prevents it. But together they form a more complete type of intelligence, one that can both predict and remember. And in credit governance, that means that PD and EL stay grounded, even as those conditions start to shift. Continuity becomes resilience. As shown in the comparison, topology transforms memory into resilience. Episodic ML forgets and relearns, while continuous graph reasoning remembers and adapts, evolving without having to have a reboot. Topology doesn't just record behavior. It doesn't just record relationships. It expresses behavior. Even when data is sparse, as we have in some cases, structure still endures where features may fail. Probability of default becomes a reflection of structural stability. Expected loss captures not only exposure, but also recovery, but the continuity of the network around each entity as well. Every shift in topology carries economic meaning, a signal of resilience or contagion, a direct bridge between mathematics and governance. And in this diagram, topology reveals behavioral communities that maintain decision stability, with PD as a function of structural stability, explainability built into that geometry. Finally, when decisions remain current, governance remains sovereign, core to financial institutions. As markets move, that topology can recalibrate probability and that loss in real time, protecting both the yield and the integrity. Explainability isn't just compliance, it's also confidence. Machine learning really allows us to capture outcomes. Topology allows us to preserve that understanding. And of course, for massive graphs, it's very, very important for us to balance computational costs using efficient approximations to scale without losing that precision. That's also important. For decades, financial institutions have been the custodians of continuity, preserving stability in an unpredictable economy. This architecture honors that stewardship, a system that learns as responsibly as they govern. Structure is that continuity, and that continuity is that governance. Thank you.